Hi, last talk of the day. I'm going to tell you a few things that are pretty general and apply to any company. The unique thing about Salesforce here will be this size. So, not sure how much you know about what Salesforce does. It's a company in San Francisco that has those high-rise towers built, and it throws a big party called Dreamforce, which is coming up in a month. But it also does software, in particular customer relationship management software. It was the first one to introduce in the cloud in 1998, I believe, 20 years ago, and it's still the largest vendor. So basically, it's a big black box that runs pretty much everywhere in the world and spits out a lot of logs. So that's what my talk will be about. One thing that might be true to most of the companies these days is that they tend to grow exponentially, but their log infrastructure is evolving organically. And typically, it is some sort of a big lake with logs and indices on top of them. And users can only perform ad hoc queries with significant delay. Like some companies use Splunk, other companies use ElasticSearch, but logs are typically not available real time. And if something happens with application performance, which is one big use case for log analysis, then it is already too late to start looking at the logs. The problem might be gone. And often the logs themselves might be already obsolete and gone from the storage. At a certain point, Salesforce realized this is a problem. And customers started to create tickets about the performance of Salesforce UI. This was one of the components that was the most complex. And we decided to do a little experiment. Can we do log analysis in real time and automatically detect problems as they still happen? So it turns out that this is a completely new approach and requires a different architecture. So let's see what we have. First of all, we start with a logs firehouse. So typically, it's some kind of a big Kafka cluster that processes all those logs. Just to give you an idea of the size, some companies have it in the range of like 100 megabytes per sec. Salesforce is typically in the range of tens of gigabytes per second. Logs are either semi-structured or fully structured, and there could be hundreds of schemas. So each schema is a Kafka topic, and we need to be aware of those schemas and apply them as we parse logs. And because there's so many different schemas and Kafka topics, for analysis, we need to join those logs. And that's one of the hardest problems in real time. So imagine that you have one source which already received the log line, but it needs to wait for another source, and the relevant log line that needs to be correlated is not there yet. So the question is, how long do we wait? This is where Flink actually has a lot of value to offer. Another challenge is that typically logs contain scopes which can be quite dynamic and high cardinality. So if you think about a global application, it may run in multiple regions, geographic regions, and within each application it could be services, hundreds of them with different application IDs, and each service may have a different release, and so on and so forth. So these are dimensions, and they could have very large cardinalities. What it means is that if you want to do analysis per scope, that means that you have to do some sort of big key buy operation, and then you will have a lot of micro partitions. And your analytics need to be running in every micro partition, and this is a challenge to do in real time. So it's another area where Flink has a lot to offer. The other two challenges, if we concern ourselves with application performance monitoring, which is one of the largest use cases for log analysis, then the application performance dynamics is often quite volatile. So most of the time, it's business as usual, everything is fine, but then something happens, and there is a volatility in application performance, and it might be gone maybe in half an hour or an hour. So if we build some sort of statistical model that would analyze some particular metric around it, that statistical model may not apply the period of volatility. So it means that the models need to be learned online. So offline models probably are not very effective at detecting any problems. And finally, there is very little value in building supervised models here. We actually played with this idea. First of all, how do we even get labeled data from our users? It means that there should be a historical sample of some cases that were addressed and resolved, and typically this sample is hard to obtain and small. And second of all, since then everything has changed. It's a new release, and those don't apply. So the only hope is actually to build unsupervised analytics. So they don't require any labeling of any kind, but the array of methods is much smaller. So these are the 4 challenges, right? We actually spent a lot of time thinking how we could actually build it at the scale of a company like Salesforce. One thing that was clear from the beginning is that to address the first 2 topics, we probably need a distributed stream processor like Flink, right? So again, real-time joins and those analytics that we want to build, including online learn, they're typically stateful. So, and Flink has those windowed operations. I'll spend the entire slide on them. This is probably how you want to start running and eventually evolve towards more complex. But another thing is, within a company, there's many different teams that require completely different results for their application monitoring. Basically, you should start thinking about multi-tenant approach if you want to build a platform for log analysis. Because one set of models and maybe even one set of views to see the results is not enough. So another use case will show up and you'll probably have to redo everything. So we decided to build a multi-tenant platform. I'll actually go into details how we do that with Flink. If you go multi-tenant, basically you should be building something that is very generic and configurable. And there should be a more or less automated process how you onboard new tenants. So there's a new team or a new client with their own set of logs, their own unique models, how they can be onboarded and start running fast, right? So statistics and analytics. Typically, you would like to do some kind of performance metric analysis just to display them on a dashboard. And you also want to have some detection models, like anomaly detection, right? You can start simple with those key time window analytics. I'll actually talk about it. But in order to do anomaly detections, soon you will realize that you need a little bit of machine learning. The important thing here is, because it's a multi-tenant platform, basically each tenant has their own set of data and their own models. So you realize that you actually need to build an automatic machine learning, AutoML, as people call it these days. So your pipeline that trains and delivers models should be running specifically for each tenant. So again, another challenge. And the number of models that will be trained and served will be in the range of millions. So it means that there will be hundreds, if not thousands, models being trained in parallel, and there will be a big repository of model metadata and some offline storage where the model states will be delivered. The most important thing in this whole architecture actually is the presentation of data. So think about logs and all those alerts that you can create on top of them. They're actually not really presentable to a user unless you think about how to make it visual. Because in the end, it's still the user that will work with them. The most common use case to start with is that they probably want to be alerted whenever something bad happens. But alert may arrive as a PagerDuty notification or an email, but it needs to take user to a dashboard. And at the dashboard, we need to present all the facts in a compact format such that there is at least a high-level overview of what's going wrong. So you will be thinking about which charts to put on that dashboard, how to customize it to each tenant, and whether you can do any sort of high-level root cause analysis, which turns out is pretty difficult. Another use case is that many teams want to do what they call A/B testing, especially across multiple releases. So what if this new release is a regression and we start to do it pre-prod testing? Can we actually have some kind of a dashboard that will tell us if there's regression in any feature or improvement, and in which particular scope the improvement or regression is? So this reminds of a business intelligence with some sort of pivoting views, where users should be able to drill down and see the results. So basically, we need to build not one, but multiple views. And that's how users will judge if the product is good or not. So this is what we ended up building, and most of it is actually Flink jobs. So because it's a multi-tenant platform, we have to define a set of generic jobs that can be configured per tenant per their use case. It basically means that there is a piece of configuration that we call manifest, and the job can take this manifest without any new code. We do allow new code to be used by users, but typically these are models, not the Flink jobs. And the first thing that you want to do is log parsing. So this is where you would like to know which schemas users is interested in, which topics, and how they can be parsed to extract the data that the user really wants. So there's nothing really challenging there, except that the configuration should be fairly generic, right? The second thing is joining. I mentioned that typically logs arrive through multiple topics, and there's a delay. So if you're doing real-time joining, it means that your stream processor, Flink in this case, will have to manage the state of the join. It's temporary, but it's fairly large. So think about the set of workers that will need to support this, and how long you would like to have that state. And what if we cannot complete the join? Should we proceed with partial join or not? The third step is what we call augmenting. Augmenting is the first step where we actually start delivering value to the end user. So augmenting is a step where we actually put a lot of small analytics that augment the parsed data with new information. Typically, these are some sort of derived performance metrics. And this is where we start to apply in scopes, and we do a key buy. And this is where we start using those rolling time windows. So if you key buy and do a rolling time window, within a time window, we can compute whatever we want, actually. Flink allows you to plug in your own libraries there, and you can just compute the averages or percentiles, or you can do some pretty complex things there. Like I can tell about use case where we actually use statistical sketches, and we do some sort of classification to see where some scopes are already abnormal or not. But the end result is there is new data computed and being added to the schema. After that, there's two separate pipelines. The pipeline in yellow is semi-online, and this is about model training. So in our platform, we have models that can be trained online and models that can be trained offline. Online models, they're typically simple analytics that are trained within Flink runtime directly. Again, think about those window operations. If your window is quite large and you have time to train your model, then you can actually run algorithms right there in Flink, okay? Offline is something where you actually cannot perform it online, and you have to collect data and run your training job in another cluster. In our case, this is a Kubeflow cluster where we typically use TensorFlow to train the data. The end result is the models are trained and delivered to a model repository, and Flink has a view of that repository in terms of the model metadata, because the models are being registered, and Flink clients that actually do inference, they know about models metadata. So inference step, which is the next pipeline, which is real-time, it's running in Flink, is actually quite simple to do in Flink. So Flink has a notion of connected streams, so you can connect the streams of model metadata updates and the stream of events, and your model metadata will be reflected in Flink client state, and whenever we need to do an inference request, we can extract the model metadata from the state and send the proper request. And the requests are typically served to an inference server, and there's a lot of good frameworks how machine learning models and analytics can be deployed as an inference servers. We don't need to build anything ourselves these days. We just need to enable a client within Flink. And we typically use gRPC framework to do that. Finally, as we have the results back from inference, we need to start aggregating results. If you run your models per event, you typically want to deliver alerts in aggregation. So there should be many events in a particular time window to trigger significant detection. And finally, there is storage and presentation. So multi-tenancy, let me go briefly about this. If you start building multi-tenant, you would like to go elastic. It means that some tenants can be small, some tenants can be large. And within Flink, it's very easy to build multi-tenant processing. So if you deploy a Flink on top of, let's say, Kubernetes or Amazon EMR, then Flink runs this additional component called application master. And you can run an application master per tenant. It means that every tenant will have its own little Flink cluster. And then you can scale the resources automatically at the tenant level. We built a lot of infrastructure code for DevOps to onboard tenants and deploy their configuration. So it basically means that there is some repo with their manifests, and any extra, like the models, that needs to be attached to the Flink model. And we have a release process that can actually start running the new release per tenant automatically. Let's go next. So those window statistics, I think it's one of the most powerful features in Flink. So first of all, Flink can do key buys on a very large key state. So in case of those high cardinality scopes, that could be millions or tens of millions of different keys. And Flink maintains the state of a time window, and typically it's an aggregated state. So it's not a sequence of events. You define your aggregator, and it's typically a number. So let's say some rolling average or something like this. And it is fairly generic. You can plug in your own analytics. So we started as simple as computing a quantile per scope. And based on this quantile, we were doing anomaly detection. Very simple model. Basically means that 5% of your events will always be anomalous, which may actually not be true. So, but then we decided to go ahead with the next version of it, which is we started to use multiple sliding windows to detect when regime shifts. So some scopes go from being good to being bad, and we have a little classification problem to solve there. And right now, it has evolved to the state where we actually try to aggregate the scopes so that there is a set of good scopes, and there's a baseline performance for them, and a set of what we call outlier scopes. And we can actually use separate statistics for those outlier scopes. But most of the scopes, 99%, are actually good, and we don't need to have a separate model for each of them. We have one model for most of them. And then this 5% actually is mostly attached to outliers as they begin being outliers, which is the most valuable moment. So your scopes are good, but something started to happen. The simple keyed window analytic detects that there is a shift, and then the scope falls out of the base into the outlier, and we trigger an alert. So same analytic, just a slightly more involved way of computing it at different scope level, and this 5% approach starts to work, even though before it was very questionable. Automatic ML. So at a certain point, you would like to go ML. We had one tenant who wanted to have some sort of a dependency graph to explain the anomalies. So think about some long-running bootstrap process that consists of multiple stages, and one of the stages may go wrong, and the tenant wanted to know which stage, okay? And being wrong may mean actually different things. It may be running significantly longer, it may be running in a different order, so there should be a robust framework how to detect this. So if you start looking at the literature, you realize that there's lots of papers, but they all require some sort of an algorithm. This algorithm is too expensive to run within the time window approach of Flink, so it should be done in offline. So we started building our own ML infrastructure at that point. And turns out that integrating it with Flink was very easy. So most of the time we spent was actually building those models. And this connected streams approach works pretty well. And Flink offers lots of facilities how you can invoke the inference server efficiently in runtime. In particular, Flink async map is the simplest one to start with. Basically, if you have an async IO where you send a request and you get a future back to Flink, then you can have many futures in flight. And typically, inference servers allow some sort of a bulk API processing where multiple requests can be processed at the same time efficiently. So this plays very nicely with the Flink async map. Data presentation. So that's my last slide. Let me spend a little bit more on that. I mentioned that this is what the user sees, right? I think this is the part that needs to be done to perfection. Monitoring dashboards, this is the first thing that pretty much every tenant requires for application performance analysis. And they all use different software for this. Some of them might come to you and say, hey, just deliver it to my Kibana or Grafana. Others say, we would like to build our own dashboards. And some users don't know what they want, right? So the question is how to support this flexibility. So we spent a lot of time on this. So what we ended up running is that typically they have a bunch of search queries that they would like to use. And whenever we create an alert, it's one particular type of search, and users immediately start to searching for more alerts like this. Second, they would like to visualize all the data that we have on those alerts, and this is some sort of a kind of a expanding tree widget, and they would like to see some progression over time, which is typical charts. So we created a generic dashboard template in Kibana, and we offer this dashboard per user automatically. But the same approach works with templated emails or templated custom templates if users want to integrate it with their own dashboarding software. So templates, basically, this is the approach. But another big use case is BI software. Again, this is a semi-offline analysis, so users may do it per experiment if they are running a, let's say, pre-staging testing. What if this really is a regression? Or they may actually do daily reporting, or they may actually go and check it every hour. Depends. But what we would like Flink to do is to deliver this data to a real-time BI data store. In our case, this is Druid. And we would like to offer a pivoting dashboard on top of it, so the users can start drilling down and see the results in more details. So the extra things that we added on top of Druid is, Druid typically starts with just a single number, and then the users start clicking on dimensions and drilling down. We actually offer an expanded view right away, and this is what we call smart grouping feature. So we have a model that analyzes which particular dimensions are of the most interest to this particular event that happened, and we draw what we call a heat map. So heat map means that it's a 2D table, and those smart group dimensions, they're colored red and green, depending on whether they're good or bad. And users immediately see something interesting, and they typically start to go towards the data that we would like to show them, not in a completely random way. So it's basically a structured journey through dimensions instead of a random walk, okay? One last thing that we incorporated was user feedback. So with all those little models, users often would like to know what kind of thresholds are applied. How do we mark a particular event as an anomaly? And we start by exposing those thresholds to them, and we now allow them to override them at a certain scope level. So your models will never be perfect enough, so you need to leave room for a manual override at certain scope level where the user thinks are special. And they can create manual thresholds and basically override a part of our model state so that it's fine-tuned towards their needs. We can also start taking feedback if our alerts are good or not. I'm not sure how fruitful is that, because that data is getting obsolete, but we'll do experiment and we'll know. So this is still an evolving project, and that's what you can do with real-time anomaly detection. All right.
Maybe one from my side. What were the biggest challenges you guys faced when implementing this with Flink?
I think the biggest challenge was joining. And this is something that I think cannot be avoided. So it's outside of our control, because this broker infrastructure is something that we don't control. And some data may simply arrive late. So the only control that we had is, should we proceed with a partial join or not? And we decided, yes, we should. And in this case, we actually apply a little bit different analysis, more coarse, but we still want to produce some data. We typically sacrifice the root cause analysis, which is the one that requires most of the joins to succeed. So in this case, root cause analysis will not be available, but users at least will see if there's an anomaly or not.
How do you let your users configure the different rules? How does it integrate in the system? Do you use like Flink SQL features, or build the pipeline, or each? So the user makes queries, you said. So you build a Flink job for each, or how do you do it?
We actually decided to go with a simpler approach. So we have a component, the first component in the pipeline called parser. And parser has a pretty long manifest, which is a piece of YAML configuration, where users can customize which schemas and which topics they would like to use. So that already filters the firehose. And they can apply their own custom transformers. And in the end, the results are transformed into a custom message format that the user defines. So we actually let users on board with their own custom schema and register their schema. So then downstream, the models that they have can actually work with their specific fully structured format. So this is mostly based around protobuf registration and custom transformer code and supporting manifests per user. And what happens if a new user onboards is that they are taken to a repo where they can visually edit and upload their manifests per job type. This is saved, and then our release process automatically picks it up and deploys. It's all versioned so that you can all see which kind of version of their configuration they are running with. It boils down to creating a lot of DevOps tooling for onboarding, which is quite doable, actually.
Okay, one more question.
So when you refer to user, you mean internal users or your customers?
So we typically our users are internal teams within Salesforce. That's what we call tenants. And specific users are performance analysts. They are performance engineers who are domain experts. They often work under tight time constraints. So they want to quickly filter and find that hay in the needle. So they are our users.
And how many users are you talking about?
I think it's about a few hundreds right now.
Okay. Thank you.
All right. Yeah, I think that's it. Let's thank Andrew again for his great talk.